Yesterday we had Jesse on Link. Pieter is Jesse's colleague, taking us further into the world of soccer, football. Floor is yours.
All right, thank you. Today I'll talk a bit about challenges, approaches, and lessons learned during the development of sports analytics models. This talk is actually based on a paper that I wrote, I think, last year or maybe already 2 years ago with a few colleagues at KU Leuven, including Jesse Davis, who talked yesterday. So I think I'm stating the obvious if I say that sports has become increasingly data-driven. Nowadays, there are large volumes of data about both the physical performance of players as well about their technical performances during games. And as the complexity and volume of this data grows, machine learning is increasingly used as an important tool to analyze this data. It's used in player recruitment, match preparation, and to analyze the fitness and health of players. So at least in soccer, sports analytics is increasingly becoming basically a subfield of machine learning. And I don't know if you've ever attended a machine learning conference, but typically about every presentation at the machine learning conference ends with a slide like this, where the author compares his approach with a bunch of baselines and other approaches to show that his approach is the best one. However, you rarely see these kind of slides at sports analytics conferences. And I think at least one reason for that is that sports analysts don't care that much about evaluation. And actually, I think they should care more. So evaluation is definitely a bit underappreciated in soccer analytics or sports analytics in general. And one good example of that is the multitude of possession value frameworks we have in soccer analytics. So these are frameworks that value how much a player contributed to winning the game. And in 2019, we proposed the VAPE framework at KU Leuven, and then you have data companies like StatsPerform, Opta that proposed alternatives to this framework like possession value, OBV. There were also some practitioners that proposed their own framework, but none of them really evaluated their approach. So everyone made small changes to the original framework, but no one evaluated it. And nowadays, we don't really know which one is better or what the differences are between those frameworks. Evaluation in the context of sports also comes with a few challenges, but that also makes it interesting. For example, a lack of ground truth. We don't know the tactical plan of the opponent. There are noisy features and labels. There are a bunch of errors in the data typically. The data is non-stationary, so players get better over time. Teams change all the time. So in a sense, we have quite small sample sizes for a single player or a single team. And finally, there are interventions. So yesterday we had this talk by BeerMind about detecting when a player is at risk of getting a concussion. I actually hope that teams take players off the pitch before they get a serious concussion. So that means that you don't have clean labels for concussions. And that's definitely a challenge when you want to train a machine learning model. And then finally, so typically if you evaluate a machine learning model, you're mostly interested in the accuracy of that model. But in the context of sports, we're also interested in other qualities, like what you eventually want to do with the model should be useful to practitioners. The results should be unbiased, they should be intuitive, they should be robust. So evaluation in the context of sports goes a bit further than typical evaluation in the context of machine learning. So the goal of this talk is basically to give you some insights in how we can evaluate sports analytics models. And I'll split up this talk in two parts. In the first part, I'll talk about how to evaluate the model itself. This is about answering questions like, does the model behave as expected? Is the model sufficiently accurate? But then what distinguishes sports analytics from typical machine learning research is that typically you're not that interested in the output of the model, but more in what you build on top of that. For example, you can have an XG model, but then you typically build metrics on top of that XG model, like you want to measure the finishing skill of a player, or you're interested in certain patterns like the build-up patterns of a team, or other outputs like a similarity vector that describes the playing style of a player. To be generic, I'll refer to these three things as indicators in the rest of my talk. And As well as the model that should be evaluated, also these indicators should be evaluated. Here we're interested in answering questions like, do they provide new insights to the practitioner? And does the practitioner understand and trust them? So to make this distinction very clear between the model itself and the thing you built on top of it, I think expected goals is a pretty good example. So the model itself is basically a binary classifier that tries to predict, given a shot from a certain location, what is the probability that that shot will result in a goal. And then on top of that, you build an indicator. For example, in soccer, we have built, we often analyze finishing skill based on expected goals. And there the idea is that expected goals represents the probability that an average player would have scored a shot. So if your player scores more goals than his cumulative expected goal value, then he must be good at finishing. So let's start with evaluation of the machine learning model. And this is not that special, but like from a methodological perspective, there are a few challenges with sports data that you have to take into account during the evaluation of your model. And because of these challenges, the naive standard methodology may not always be appropriate. For example, during the evaluation, the bedrock of evaluating a machine learning model lies in the use of an independent test set to make sure that your model can generalize to unseen examples. Typically, it is done using some kind of cross-validation scheme where you split the data randomly into faults and then evaluate on the faults. The problem is that sports data are not independently and identically distributed. So that doesn't really apply typically to sports data because, first of all, there are temporal dependencies. So on the physical side, sessions are planned based on what a player did in the previous session and what will happen in the future sessions. You're not going to give a player a hard session the day before a game, for example. Similarly, seasons are ordered, matches are ordered within a season, and events in a game are ordered. And like the thing with temporal data is that the changes from one observation to the next are typically not sufficiently big so that there's a big correlation between successive observations. There's also subject consistency. So if you test the same subject multiple times, then he will act similarly between sessions. And therefore, if you would randomly split the data using a typical approach, you can't really be sure whether you're actually just predicting a proxy or whether you've learned something meaningful. There are other subtle biases. These are especially coming because good teams and players tend to engage in more actions. Again, let me take expected goals as an example. So as I said, expected goals models are typically used to estimate finishing skills. And that is based on the premise that expected goals represents the probability that an average player would have scored a shot. But what we found is that actually good players tend to shoot more, and that's what you can see on the image over here. So we took the 20% of players that take the least amount of shots, and then, for example, here in this zone between the penalty spot and the border of the penalty area, they would score 9% of the shots from that zone. While if you take the players that take 20% most shots, then they score 15% of shots from that region. So that's quite a big difference. So what you can see in this is that expected goals doesn't really represent the probability that an average player would have scored a shot, but it's more probability that an above average player would have scored a shot. And then if you would use that to evaluate finishing skill, you're basically underestimating the finishing skill of the good shooters. Then the second takeaway that I have about this is actually quite obvious, is that the evaluation metric should be tailored to the use case of the model. But actually what you see here is that still people make quite a lot of mistakes about this. And then the most typical mistake is that they use a metric like the ROC, the area under the ROC curve to evaluate probabilistic classifiers. There is actually like a part from a paper that I read where they argue that like the area under the ROC curve is the best metric to evaluate expected goals models because it can deal well with imbalances in the classes. And that's obviously right, but the issue is like in like unexpected goals models, you're not really interested in the classification itself, but you're more interested in the probabilities. And let me illustrate that with an example. So in soccer, about 1 in 10 shots results in a goal. So let's say that we have 10 shots, 1 of them resulted in a goal, the first one, and then the 9 others were a miss. And then we have 2 models. A first model, which is extremely confident and which gives a probability of scoring above 95% to each shot, but correctly gives the highest probability to the shot that resulted in a goal. And then we have a second model, which gives a bit more realistic probabilities, but doesn't give the highest probability to the shot that resulted in a goal. Then if we compute the area under the ROC curve for those models, then you can see that the first model is by far the best one. But the issue with the ROC score is that it doesn't really care about the probabilities. It only uses the probabilities to create a ranking and then throws away the probabilities and then checks whether the shots are correctly ranked such that the shot that resulted in a goal is on top. A way better metric to use for these kind of problems is the Breyer score, which is basically the mean squared error and which takes into account probabilities. And with this score, like model B is clearly better because lower is better here. So with Breyer score, you get an error score, but there's one issue with it. It's not very interpretable. So like it's not very obvious that a score of 0.08 is good here. There's a solution for that as well, which is the normalized Breyer score, where you divide the Breyer score by a simple baseline. And here, the simple baseline can just be predicting your prior probability. So like that's 10% of the shots result in a goal. And you can see that model A, like that model that is extremely confident, is actually 900 times worse than the baseline model, while our model B is about 11% better than the baseline. So this is where the typical evaluation of machine learning models ends, but I think we should go one step further because these aggregated metrics, they are definitely very useful, but they don't really allow you to understand how the model will behave in very specific situations. These are examples of questions that someone might have about a model, which you can't answer with the typical evaluation metrics. Like, what is a model at risk of misprediction? That is, are there certain regions of the instance space where the model might make more mistakes, for example, because there's not enough training data for like rare situations, or because the data observed during training differs a lot from the data observed in practice? The second question might be whether the model is robust to small changes in the input. For example, if you slightly change the time in the game, that shouldn't have really an impact on the output of an expected goals model. And third, does the model behave as expected for certain scenarios? For certain scenarios, we might have a strong intuition about what we can expect. For example, if you shoot from a very tight angle, then the expected goals probability should obviously be very low. So to answer these questions, we need to reason about the model. And more specifically, what we need here is verification. I'm not sure whether everyone is really familiar here with verification, but like the most famous application of verification is a generation of these so-called adversarial images, where you try to trick a classifier in giving a certain output. For example, you show the classifier an image of a panda, and you want to predict it as a gibbon while slightly changing some of the pixels. But more in general, verification is about reasoning about the model to generate more insights into how it will behave in practice. Another way to look at verification is as the inverse of prediction. So again, let's take the example of expected goals, where we want to predict the probability that a shot will result in a goal, and we represent that shot by a number of features like its location, the distance to goal, and the angle to goal. And then we want to predict that probability with an ensemble of decision trees. So therefore, I guess everyone knows this, we sort the example into the leaves of the node and then take the sum over the leaves. So that gives us a probability of 4.5% to score from this shot. In verification, we basically do the opposite. This time, we want to maximize the probability of scoring a goal given a number of constraints. And here, the constraints define that the shot should happen from outside the penalty area. And then to answer this question, what we have to do is we have to go from each leaf to the root and see whether there's a path that satisfies these constraints. Then if we find multiple paths for one tree, then we take the maximum leaf value. And then we can find here, for example, that there exists a shot that satisfies these constraints. So that's outside the penalty area with a 5% probability of scoring. The thing here is that it's way harder than the prediction task because it is actually an NP hard problem. But if we can like optimize some things and do things cleverly, then we can use this to answer some like really interesting questions. What we did is we applied this verification approach to one of the models that we developed at KU Leuven, the VAPE model, which predicts the probability that a player will score within the next 10 actions. And then we actually found quite a lot of interesting things. I'm not going to talk about all of them in this presentation, but like we wrote a blog post about it that summarizes it a bit. And one thing maybe to highlight here is something interesting that we found is one of the features in the model is the current time in the game. And then what we found there is that somewhere around the 25th minute in the first half, you can basically increase the probability of scoring from any action by about 20%, just going from 1 minute to the next minute. So that's clearly a bug in the model, which we had never observed just using the aggregated metrics. But if like a practitioner would like encounter this kind of prediction in real life, he would really lose his trust in the model. So that's why like these kinds of detailed verification of the model can be really useful. So then in the second part of my talk, I'll talk a bit about validation, which is the often overlooked aspect of evaluating a machine learning classifier in the context of sports. And validation is essentially about testing whether an indicator can provide value to the workflow of practitioners. So it's essentially testing whether your indicator can fulfill the needs of your users. And in contrast to the evaluation that I've talked about before, there are no real guidelines or rules about how to do validation, but I think we can get some inspiration from usability testing and software design here. Because just like validating an indicator, usability testing is about making sure that users can find value in what you're providing to them. And typically, this is done by interviewing or observing users while they use a product. So people have come up with various criteria to check when validating how valuable a user interface is. And actually, I think a lot of these can also be applied to sports analytics. For example, in his famous user experience honeycomb framework, Pieter Morville defined criteria like that it should be desirable, credible, and useful. And this can equally be applied to sports analytics. So inspired by that, we came up with 4 criteria for a valuable user interface, for a valuable indicator. The first one is that it should be insightful. That is, it should provide insights that are not already readily available. For example, expected goals tell you something beyond the number of goals scored. It tells you whether a player was able to get into good scoring positions. Then it should be intuitive. That is, it should be easy for non-machine learning experts to understand, and therefore it often helps if it's based on concepts from the sport. Third, it should be credible, which often boils down to being able to contextualize when the metric is useful and making sure that the values do not wildly fluctuate. And finally, it should be actionable. That is, practitioners should be able to do something useful with it. So I think none of these criteria aligns with the standard evaluation metrics used in machine learning. So in the remainder of this talk, I'll try to give a bit of an insight into how this can be approached to evaluate them. First, to evaluate the credibility of an indicator, there is what most people in soccer analytics would probably know as the Messi test. But in the literature, it's known as face validity, which looks at the extent to which a test is objectively viewed as covering the concept it purports to measure. So basically, it's about testing whether your metric makes sense to practitioners. And this is especially relevant for evaluating the offensive performance metrics, because typically people have some intuition about who are among the best performing players. For example, when considering Messi and Ronaldo, there is some debate among fans about the relative merits of these players, but basically everyone would agree that both Messi and Ronaldo were among the top offensive players in the past decade. So when you design a metric and neither Messi nor Ronaldo is at the top of your metric, then there's probably something wrong with your metric. As an example, a few years ago, The Economist looked at which players ranked highest according to our vape metric. And then they found that Messi was on top, followed by Ronaldo and Neymar. So you could say that our vape metric passed the Messi test. To be credible, it's also important that a metric has some kind of robustness in its values. That is because most metrics are designed to measure some kind of skill. And while skill definitely evolves, like players get better over time, and when they age too much, they get worse again. But like within a shorter period of time, like the skill of a player shouldn't be too different. So for example, within a season or even between seasons, the value of a metric should be quite stable. And one approach to measure this is to split your data set in half, then compute your metric on both halves, and finally compute the correlation between the outputs on both data sets. If the correlation is high, then your metric is robust. So to illustrate this, we looked at a few common performance metrics in soccer analytics. So what we did is we looked at 10 consecutive Premier League seasons and then computed the correlation between the metric for two pairs of seasons. Each dot represents one pair of seasons, and then the diamond shape is the average over these 10 seasons. And then you can see that the metric, like the minutes played of a player, has quite a low robustness. That is because it's influenced a lot by things like cards, injuries, and roster changes. Expected goals had, according to me, a surprisingly high robustness. And then the other ones are possession value metrics. I think the interesting thing here is that our vape metric had a quite low robustness value, and that was mostly due to shots. Because like shots really influenced the value of that metric, while the outcome of shots is very quite random often. Then second, a metric or an indicator should be able to provide new insights. And I think on this aspect, a lot of papers miss the point a bit, because in their evaluation, you often see that they will focus on achieving a high correlation with existing metrics. This is actually an excerpt from a hockey analytics paper. But I think that any paper that strives for a high correlation with existing metrics misses the point a bit, because the goal of designing a metric is to come up with new insights that existing metrics cannot provide yet. And like a high correlation is exactly the opposite of that. Then an indicator should be intuitive, so experts should be able to understand it, and therefore it helps if it's based on domain knowledge or concepts that practitioners are already familiar with. For example, when building a model to predict the value of a pass, I think it's a good practice to use features like whether there was pressure on the player playing the pass, whether the pass was a line-breaking pass. So if you design a model, I think you should always base your game state around concepts that practitioners are familiar with, instead of just like using the raw XY locations of the players in a deep learning model. Similarly, it should be possible to explain the output of the model to practitioners. And I think a great example here is the expected threat model, which is based on quite a complex recursive equation, but then the output of the model is like very easy to explain to practitioners. That is, it predicts for each location on the pitch the probability that a player would have scored within 5 actions. So that's like very easy to understand. And then finally, an indicator should also be actionable. And I think there are 2 ways in which an indicator can enable this. First, by saving time in the workflow of practitioners, or alternatively by providing relevant, concrete information that an analyst can do something with it. One workflow where I think machine learning can really save time of a practitioner is in auto-tagging match situations. So video analysts spend a lot of time watching video to annotate specific events, technical principles and outcomes, but a lot of these can actually be animated with simple machine learning. And then on the right, there's like, I think, a pretty nice example of like how an indicator can provide relevant insights. This is from a paper by Javier Fernandez, where he tried to figure out like how you should defend against a buildup of Liverpool. So basically, therefore, you have to identify like where Liverpool creates most danger by receiving passes. And then what he did there is they used his possession value framework to see like which formation can most reduce the threat from receiving in certain zones. And then they found that the 4-3-3 is the best formation to defend against Liverpool. So that's a very concrete and well-motivated insight. So the thing with validation is that some aspects of it can definitely be evaluated qualitatively, can be evaluated quantitatively, but most of it is still a qualitative evaluation. So it really involves getting experts involved, which can be quite hard because they have a tight schedule and competing priorities. But getting experts involved, especially early in the process, can really help to validate some assumptions, to improve the methodology, and will almost always in the end lead to a better indicator. So in conclusion, the point that I wanted to make is that evaluating learning systems in the context of sport is challenging, but it's definitely worth to spend attention to it. And it requires both evaluating models and validating indicators. So evaluating the model itself is in a sense not that special, but there are some specific challenges in the context of sport that you should be aware of when doing the evaluation. It's also important to evaluate the evaluation to the use case of the model. So don't use the area under the ROC curve to evaluate a probabilistic classifier. And like if you really want to understand how the model will perform in practice, you should reason about the model. And then for validating the indicators, we've proposed 4 criteria that should be validated. They should be insightful, intuitive, credible, and actionable. And this requires interaction with domain experts. That's about everything that I wanted to talk about. If you're interested in this, there's a lot more stuff in the paper that we wrote about it. And I'll finish with like one small advertisement. In September, I'm organizing the Machine Learning for Sports Analytics workshop in Porto. It would be great to have a few ice hockey analytics papers there as well. The deadline is very soon, though. I think it's the 15th of June, so that's less than 2 weeks. But we also we also accept extended abstracts, which can be of published research. So that should be doable to write in 2 weeks.
Indicators that you've taken here that they should have, is it different at all for different sports? So for soccer as comparison to hockey, or can we say the model that you're proposing should go over all sports?
Yeah, when we wrote the paper, most of our examples came from soccer, but we really had other sports in mind as well. So it's definitely tailored to team sports. I wouldn't say it necessarily applies to running, for example, but like I'm sure like for ice hockey, you can use the same criteria.
And you also said the practitioners, in other words, the coaches or the actual players don't have time. Wouldn't it be smart for them to make the time?
Yeah, I definitely think it would be smart for them, but like it's like about building a relationship with coaches. I think like coaches don't always have that analytical mindset. They often come from the game itself.
And they don't trust the numbers, and they don't trust you.
Yeah. Okay. That's often the
same problem that football and hockey there is probably very similar. I don't know if there's a comparison who is more open. Thank you, Pieter.